Hello, everyone, and welcome. I'm Amna, and it is an absolute pleasure to have you here with me today. Have you ever held a tiny pill in your hand and just marveled at the science behind it? How does this small, simple thing know exactly where to go in your body and what to do when it gets there? How can it possibly ease a headache, lower your blood pressure, or fight off an infection? It feels a bit like magic, doesn't it? Well, today we are going to pull back the curtain on that magic. We're going to explore the incredible world of pharmacology, the science of how drugs work, and I promise you, by the end of our time together, it will feel much less like magic and much more like elegant, understandable science. Let's start with the big picture. Pharmacology is simply the study of substances that interact with living systems through chemical processes. These substances bind to special molecules in our body and can either turn on or turn off our normal biological functions. Within this huge field, there are two main branches. There's medical pharmacology, which is the wonderful science of using substances to prevent, diagnose, and treat disease. But there's also toxicology, which is the other side of the coin. It deals with the unwanted or harmful effects of chemicals. To truly understand how a drug works, we need to think of it as a two-way conversation between the drug and our body. We have two key terms for this, and they are the foundation for everything we'll discuss. The first is ABAT, pharmacodynamics. It's a fancy word, but all it means is what the drug does to the body, how does it interact with our cells, what effects does it produce. The second is BAT, pharmacokinetics. This is the opposite what the body does to the drug. How does our body absorb it, move it around, and eventually get rid of it? It's this beautiful dance between the drug and the body that produces a medical outcome. So, what exactly is a drug? At its core, a drug is a substance that creates a change in our biological function through its chemical actions. It doesn't just wander around aimlessly. It usually has a very specific target molecule it wants to interact with, and we call that target a receptor. Think of the receptor as a lock on a door. The drug is the key. When the key fits and turns the lock, it activates it. We call this type of drug an agonist. It turns things on. But what if a key fits into the lock but doesn't turn? It just sits there, blocking the keyhole so the correct key can't get in. That's what we call an antagonist. It binds to the receptor and prevents it from being activated. Most of these drugs are what we call xenobiotics, which is just a scientific term for chemicals that aren't naturally made inside our own bodies. Now, the physical nature of a drug is also incredibly important. Drugs can be solids, liquids, or gases, and this often determines how we take them: a pill, a liquid syrup, or an inhaler. The size of a drug molecule is also critical. Most drugs fall into a Goldilocks zone of size with a molecular weight between 100 and 1000. If a drug is too small, below 100, it tends to be less selective. It's like a skeleton key that can fit into too many different locks all over the body, which can cause a lot of side effects. On the other hand, if a drug is too big, over 1000, it has trouble moving around the body. It can't easily pass between different compartments, like from our bloodstream into our tissues. It's like trying to get a large sofa through a narrow doorway. That's why very large drugs, like some proteins, often have to be injected directly where they need to work. How does the drug, our key, actually stay in the lock? It uses different types of chemical bonds. The strongest is a covalent bond. This is like super glue. It's incredibly strong and often permanent. Aspirin is a great example. It forms a covalent bond with an enzyme in our platelets, and that effect lasts for the entire life of that platelet. More common though are path electrostatic bonds. Think of these like magnets. They are weaker than super glue but still create a strong attraction. And finally, there are very weak hydrophobic interactions, which are important for drugs that need to pass through the fatty membranes of our cells. And here's a beautiful little detail. The weaker the bonds, the more selective the drug has to be. If you are using weak magnets to hold something in place, the shape of the drug and its receptor have to fit together almost perfectly. This precise fit is what gives us highly specific drugs with fewer side effects. Speaking of a perfect fit, the three-dimensional shape of a drug is everything. This is where we get into a fascinating concept called chirality. More than half of all drugs are chiral, which means they exist as mirror images of each other, like your left and right hand. We call these mirror images enantiomers NDET. Even though they look almost identical, one version often fits into the receptor much better than the other. For example, the drug carvedilol is used to treat high blood pressure. Its left-handed version is a powerful blocker of a certain receptor, while its right-handed version is 100 times weaker at that same receptor. It's all about that perfect three-dimensional fit. Let's dive a little deeper into that drug-receptor interaction. Receptors in our body aren't just sitting there waiting completely off. They can exist in at least two states, an inactive state and an active state. Even without any drug around, a tiny fraction of them are naturally flickering into that active state. This creates a small baseline level of activity in our cells, which we call a constitutive activity. This is where the different types of drugs show their true colors. Full agonist has a very strong preference for the active state of the receptor. When it binds, it shifts almost all the receptors into that active state, creating the maximum possible effect. It's like flipping a light switch all the way on. Update partial agonist is a bit more ambivalent. It likes the active state, but not as much as a full agonist does. It will shift the balance towards active, but it can't produce a maximal effect, even if you add a ton of it. It's like putting the light switch on a dimmer halfway up. Interestingly, if a full agonist is already there, a partial agonist can get in the way, acting a bit like an antagonist. A conventional antagonist has no preference at all. It binds equally well to both the active and inactive states. It doesn't change that baseline flickering, but it physically blocks an agonist from getting to the receptor. It's like putting a child-proof cover over the light switch. And then there's a really neat one, the Conge inverse agonist. This drug strongly prefers the inactive state. It binds to the receptor and stabilizes it in the off position, actually reducing that baseline constitutive activity. It doesn't just block the switch, it actively pulls it into the off position. These drugs can also interact with receptors in different ways. The most common is competitive inhibition, where the antagonist binds to the exact same spot as the agonist. They are competing for the same chair. If you add more agonist, it can eventually win the competition and overcome the block. But some drugs use allosteric interactions. They bind to a different site on the receptor, not the main one. From this secondary site, they can change the receptor's shape, either making it easier for the agonist to work, which is allosteric activation, or making it harder, which is allosteric inhibition. This type of inhibition usually can't be beaten just by adding more agonist. So that's what the drug does to the body. But what about the other side of the conversation? What does our body do to the drug? This is the journey of pharmacokinetics. For a drug to work, it has to travel from where we take it, like our stomach, to its target receptor somewhere else in the body. This journey involves crossing multiple biological barriers, like the walls of our intestines and the membranes of our cells. There are 4 main ways a drug can do this. The first is aqueous diffusion, which is just moving through the watery gaps between cells. The second and most important for most drugs is lipid diffusion. The drug literally dissolves into the fatty lipid membrane of a cell and passes right through. It's the main superhighway for drug transport. The third way is through special carriers or transporters. These are proteins in the cell membrane that act like selective doorways, helping substances get in or out. Some transporters bring things into cells, others, called efflux transporters, actively pump things out. One of the most famous is P-glycoprotein, which acts like a bouncer, protecting sensitive tissues like the brain by pumping foreign chemicals out. Finally, for really large molecules, the cell can use endocytosis, where it literally engulfs and swallows the drug whole. Now, for that main highway, lipid diffusion, there is a crucial factor that determines whether a drug can pass: its charge. Most drugs are either weak acids or weak bases, which means they can exist in two forms: an unionized uncharged form or an ionized charged form. Here is the single most important rule: only the uncharged unionized form is lipid soluble enough to easily pass through a cell membrane. The balance between the charged and uncharged forms depends on two things: the drug itself and the pH, the acidity or alkalinity of its environment. A weak acid is mostly uncharged in an acidic environment, while a weak base is mostly uncharged in an alkaline or basic environment. This chemical principle allows for a brilliant clinical application called ion trapping. Because different parts of our body have different pH levels, we can trap a drug in a compartment where it becomes ionized or charged. Once it's charged, it can't easily cross back over the membrane. Imagine someone has taken an overdose of a weak acid like aspirin. We want to help their body get rid of it faster. We can give them a substance that makes their urine more alkaline. When the aspirin gets into the alkaline urine, it becomes ionized, it gets a charge. Now it's trapped, it can't be reabsorbed back into the body from the kidneys and is safely excreted. We literally trap the drug in the urine. It's a beautifully elegant way to use basic chemistry to help a patient. Let's quickly recap what we've learned. We've seen that pharmacology is this amazing two-way conversation between a drug and the body. We have pharmacodynamics, what the drug does to us, and pharmacokinetics, what our body does to the drug. We've learned that drugs work like keys fitting into highly specific locks called receptors, and that their size, shape, and the bonds they form are all critically important for their function. And finally, we've explored how the body moves drugs around and how we can use fundamental principles like pH and ionization to our advantage in medicine. I hope this has made the world of pharmacology feel a little less mysterious and a lot more fascinating. It's a field that truly combines biology and chemistry in the most elegant way to improve human health. I would absolutely love to hear from you. What did you find most interesting? Do you have any questions about what we discussed today? Please don't be shy, let's chat about it in the comments below. I'll do my very best to answer every single one. Thank you so much for joining me. Take care and bye for now.